Okay, so what I've given you is kind of a list of topics for next week's exam, broken down by chapter, and also where there's additional practice problems in the Canvas folders I've indicated where those are and what their names is. This is not a comprehensive list, so I may have forgotten something as I went through this, so if I remember that by next week, then don't. Well, it wasn't on here. This is not a comprehensive list. But it'll give you a general idea. In terms of practice problems, there are some in Canvas. There are the older exam problems. This test is going to be a combination of some of the exam 1 problems, cyclohexanes and Newman projections, and also exam 2s, which are the stereochemistry and the SN1 and SN2s. So it'll be a combination of old exam 1 and old exam 2s. For exam 2, there's free radical halogenation on those. That's not part of this exam because we haven't. That comes next semester in this textbook. Okay, so there should be plenty of practice problems for this exam that you can do to see where you're at. And if you wanted to, you could piece together a practice exam from all of those materials. Okay, so that's kind of where we're at. And we'll see. We're going to do E1, but there's a couple things I want to mop up here in terms of SN1 and SN2, starting with the table, generating a table of which reaction occurs when that we left off class with. And then talking about the role of the leaving group and the role of the solvent. So let's start with going back to where we were on Friday, or on Wednesday. So on Wednesday we said, okay, if you have a primary alkyl halide, it can only undergo SN2 because SN1 requires a carbocation intermediate and a primary carbocation is not stable. The SN2 is dependent on sterics, and a primary halide is less sterically hindered, so SN2 will occur. For a secondary alkyl halide, we could have SN2 or we could have SN1 because a secondary carbocation is stable, and most secondary halides are not sterically hindered to block SN2. And then finally, for the tertiary halide, that is too sterically hindered for SN2. Its carbocation is very stable, so it can only undergo SN1. Then for our halides, if we're talking about a strong nucleophile with a negative charge, it prefers SN2, but it will also undergo SN1 as well. So it's strong enough to come in and kick off a leaving group. But on the other hand, a weak nucleophile like water or an alcohol, those have to go by SN1. So weak nucleophiles can only react with carbocations. Okay. So that's what we know about each individual nucleophile and about each individual alkyl halide. So what we now need to do is we need to create a table where we're going to correlate, okay, if you have this halide and this nucleophile, what reaction do you get? But it's not really a question of memorization, although if you have to, you have to. But it's really about, okay, what can the halide do? What can the nucleophile do? So the way we normally set this up is we say, okay, we've got a primary halide, or actually we'll do it this way. We'll say, here's the halide. There's primary, secondary, and tertiary. And then over here we have a strong nucleophile, and then we've got a weak nucleophile. And so there's our grid. So primary halide with a strong nucleophile, what reaction is that going to be? What do they have in common? SN2. So they're going to undergo SN2. Primary in a strong nucleophile is going to undergo SN2. Now, how about a weak nucleophile? Well, since the weak nucleophile can only react with something that forms a carbocation, we're going to get no reaction for a weak nucleophile. A secondary and a strong nucleophile is going to favor SN2 because the nucleophile is strong enough to come in and kick off the leaving group. But a secondary and a weak nucleophile, since the weak nucleophile has to react with the carbocation, that mechanism is going to be SN1. It has no choice. And then tertiary is going to be what? For both. Yeah. It's going to be SN1 for both. So that's one of the sort of, when we combine these two reactions together, we're going to need to be able to say, okay, this reaction goes by SN1, this reaction goes by SN2. And this is cutting out a lot of gray area, because we're going to sort of get into the gray area, but because there's a continuum of strength of nucleophile, you can have some things that may or may not fit this chart. But this is going to be our chart that we start with. Because otherwise, if we focus on the exceptions, then there are no rules, is what I find. And I remember taking this stuff 30 years ago, and it wasn't organized well, and I had no idea what. It was just like a random guess as to what reaction occurred. And it shouldn't have been, because it's very well laid out. And then we can always add exceptions, or we can add modifications to it as we go. And I think they developed this in one of the chapters of the book as well, or in a very similar way. Okay. So does this make sense? I mean, you can memorize it, but it should, like tertiaries, got to be SN1. Primaries got to be SN2. Weak nucleophile, not strong enough, so no reaction. And then secondaries can go either way. If it's a strong nucleophile, it'll do 2. If it's a weak nucleophile, it's got to do 1, because it's got to form a carbocation. So there is a whole reasoning behind this. Okay. So in next week's exam, I could give you a reaction and expect you to figure out what the mechanism is. To say, okay, here's the mechanism, and then here's the products of that reaction. Okay. Now we need to add E1 into this, but it'll be really easy to do that once we talk about E1. Okay. All right, so is everybody kind of with me? I'll assume yes. Okay. Now, just to kind of finish up SN1 and SN2, we talked about how to look at the strengths of the different nucleophiles, right? If we're talking about nucleophilicity horizontally, what is it based on? It's okay. We'll keep everybody awake.
I have a puzzler.
Emma? Horizontally. The size of the molecule, is that horizontal or vertical? Someone help her out. Is the size of the molecule, is that horizontal or vertical? Vertical? So that's vertical, and that's what we called what? Starts with P. Polarizability. And that's size. And how does vertically, how does the nucleophile strength go? It increases when you go up or down. Down. So it increases as we go down the periodic table. Okay. Now what about horizontally? What does it affect there? Basicity. How? Direct or indirect? Meaning that a stronger base is a blank nucleophile. Stronger? Do we agree with that? I don't see many heads shaking either direction. Stronger base, stronger nucleophile? Yes. Stronger base, stronger nucleophile. Where is it inversely related? Leaving groups. So when it's leaving group, stronger base, weaker leaving group. I think we just had a quiz on this on Wednesday, didn't we? That was 2 days ago. We have to work to make it stick here, preferably more than 2 days. Okay. And I know these are all inverse relationships. So we've got to get them under control. Left to right or right to left on the periodic table. So if I have my periodic table, how does so if I have a CNOF SP Cl Br, how does nucleophilicity go horizontally on the periodic table? It's going to increase to the left. We all agree with that? So it increases as you go from right to left. And we have to know that, because after I talk about solvent effects and leaving group effects, I'm going to take a little bit of I'm not quite going to get to E1 yet. I'll get to there today and Monday. But then we can compare rates of reactions, which I saw they had in your textbook as problems that you'll have to do. So in order to do that, we need to be able to compare nucleophile strength up and down and left and right on the periodic table. Okay. Right. So we need to know this. I'm almost tempted to have another quiz on Monday morning over the same kinds of things to see if it's stuck over the weekend. But I'll think about that. Okay. All right. What's the effect of solvents? Well, first of all, we have to talk about what kind of solvents you can use for this reaction. And you have two choices. Well, you have one choice. Got to be a polar solvent. Because the reaction I'm going to do is I'm going to take a nucleophile, I'm going to react it with an alkyl halide, and I'm going to form the carbon nucleophile bond, and at best I'm going to kick off the leaving group. So this has to be a polar solvent in order to solvate the negative ions. And to solvate the carbocation intermediate. So we have to deal with a polar solvent, except there's two types of polar solvents. There are what some textbooks call aprotic, and there are protic. I've never liked that term, primarily because some of the stuff I did for my thesis involved this, and it isn't an accurate term. So I will sometimes call these ones non-hydroxylic and call protic ones hydroxylic. Because not everything that's protic, not everything that's aprotic is really aprotic. You can deprotonate things. So here's some examples. Well, give me an example of a hydroxylic solvent. The name says it all. It's a solvent with a hydroxyl group. So what would be the best one? Solvent with an OH group. Well, these are solvents. So a solvent with an OH group in it. Melanie? Alcohol? What else? Those are our two biggies. Alcohol and water. They both contain OH groups. They both contain protons that can be deprotonated, so hence they're called protic or hydroxylic solvents. Now, the aprotic solvents are things that we've used in lab. Like acetone. There's the sulfur equivalent. Which is dimethyl sulfoxide, or called DMSO. It has the sulfur instead of the carbon. We don't use that in lab. We sometimes use it for spectroscopy, but we don't use it for lab, primarily because when it gets on your skin, it goes right into your bloodstream. And anything that's with it goes right into your bloodstream too. So sometimes you would see, at least in the old days, you would see like signs on the side of the road with people saying, you can buy your DMSO here. No, I'm not buying my DMSO from an amateur chemist who isn't purifying it to the utmost quality. It's supposed to relieve pain, I guess. But if it's not purified, who knows what's going into your bloodstream. It has kind of a garlicky taste when it does that. It's been in my bloodstream before. We could have things like CH3CN, which is called acetonitrile. And so basically we have polar solvents with no OHs. Those are our non-hydroxylic solvents. And so for the effective solvents, we break it down into those two classifications. And so one of them will speed up or slow down an SN1 or an SN2. So let me show you the way to think about this. the rate determining step for an SN1 reaction is the breaking of the carbon-halogen bond and the formation of the carbocation and the leaving group, anion. Now, my choices of solvents are either hydroxylic or non-hydroxylic. So what happens when a hydroxylic solvent is used is that the hydroxylic solvent, the oxygen of that, solvates the carbocation really well. And then the H of the hydroxylic solvent solvates the anion really well. In that, it solvates it much better than a non-hydroxylic solvent will, because now we're looking at maybe forming some hydrogen bonds, or that we're solvating with more polar molecules because they have OHs. So let's think in terms of our big picture principles. Okay, my big picture principle is I want to push that reaction to the right. I want to make it occur faster. What should I do to the products? Or what should I do to the intermediates? If I want this reaction to go faster, I should do what to the products or the intermediates, Melanie? Stabilize them, make them more stable. That's what hydroxylic solvents do. They better solvate the carbocation and the anion, and so they make the intermediate, they make the products of this reaction more stable. And remember, we have the basic Hammond's postulate that says the more stable that you make the product, the lower the transition state energy, the lower the activation energy, and the faster the reaction occurs. So for SN1, it's the hydroxylic solvents cause them to go faster. Because of that better solvation. And it's not that the non-hydroxylic solvents don't solvate it well, but they don't solvate it as well as the hydroxylic ones. Does that make sense to everybody? So now let's think about SN2. In the SN2 mechanism, the nucleophile comes in, attacks the carbon, kicks off the leaving group in that reaction. So now we have to think about, well, what would the role of the hydroxylic solvents be in this reaction? They solvate the nucleophile really well, right? I'm going to have those solvents solvating the nucleophile really, really well. So what's that going to do to the nucleophile? Well, it's going to solvate it so that as it approaches the alkyl halide, it's going to have to get rid of all that solvent in order to attack. Right? It's carrying all this solvent with it that it's got to get rid of and then react with the alkyl halide. Is that going to make the reaction faster or slower? It's going to make it slower. So in this case, I don't want good solvation of the nucleophile. I want things to be kind of loose so that it doesn't require a lot of energy to kick that off to then react. So in this case, because it solvates so well, it's going to slow down the reaction. And so for an SN2 reaction, the hydroxylic solvents slow down or reduce the rate of the reaction. Because now they're doing what they're doing, but that's not what we want. That's not what stabilizes. It actually makes the reactant more stable. And you could think about Hammond's postulate. If you pull down the energy of the reactant, you're going to increase the activation energy. Okay. So I don't even worry about aprotic solvents or non-hydroxylic ones because the focus is on hydroxylic ones. They speed up by solvation SN1. They slow down by solvation SN2. Does that kind of make sense? I mean, it's doing the same thing. It's just in one case it's good and in one case it's bad. Okay. Leaving group. So how does the leaving group affect the rate of an SN1 or an SN2 reaction? It's as simple as this. The better the leaving group, the faster the SN1 or SN2 reaction. And what it boils down to here is when the nucleophile again comes in, attacks the carbon and the leaving group leaves, my transition state has the leaving group in it. So the better the leaving group, actually the lower the transition state energy is going to be, the lower the activation energy is going to be, the faster the reaction. So whenever the leaving group is part of the transition state of a rate determining step, it will affect the rate of the reaction, and more importantly, the better the nucleophile, the faster the reaction. So it's got to be part of the rate determining step. Well, for an SN2 reaction, remember, it's a one-step mechanism, so that is the rate determining step. Is the leaving group in the transition state? Yes. So better leaving group, faster reaction. What about SN1? Will the better leaving group cause the reaction to occur faster? What do you think?
Lucy Puzzle.
I think it would be like the role rate determining step of SN1.
Okay. So is the leaving group in the rate determining step of an SN1 reaction? Yes. So will it affect the rate? Yes. Better leaving group, faster reaction. So what's the rate determining step of the SN1 reaction? To break apart and form the carbocation within the leaving group. So is it part of the rate determining step? Yes. Is it part of that transition state? Yes. So better leaving group, faster reaction for SN1. So the better leaving group will affect both SN1 and SN2. Does that make sense? How about the nucleophile strength? If I have a stronger nucleophile, will it affect the rate of an SN2 reaction? We'll have some participation instead of me pushing the button and everybody cringing in fear, except for somebody who's not on this wheel. But then I could always, if somebody's not here, then they can take their place. And unfortunately, you can't participate in because I can't switch classes. So you can tell your friend or your partner there what the answer should be. I'll catch the participation for this afternoon. Okay. What was going to be my question? Oh, here's my question. Am I in the right class? Yes. My question is a multiple choice question. Will a stronger nucleophile cause an SN2 reaction to occur faster, slower, or have no effect so that the reaction would occur at the same rate? So if I make the nucleophile stronger, will it affect? If it does, it's either faster or slower. If it doesn't, then it's the same rate. So as you're thinking about that question, think about what we just went through in terms of our criteria. Faster, slower, same rate? What? Okay. Okay. I don't know why that is. Anybody else is not connecting? That wasn't my question. My question was, anybody else who didn't connect?
Mine didn't at first, and I logged off the Wi-Fi.
Okay. The Wi-Fi's messed up. Apparently the JCU guest, when I met with ITS people, I said, "Oh, by the way, did you guys shut down the JCU guest?" And they're like, "No." Is it not working? Yeah, it hasn't worked for about a month. Oh, you're the first person to tell us that. That's not good. Okay, everybody else is okay? Okay, then I've got everybody. Then what I should ask is I should ask the 3 people who didn't attach to what their answers would be. But we'll go ahead and just do this. 22 A's. What was A? Faster. Was that what everybody was going to choose? Okay. What's our criteria? Our criteria is it part of the rate determining step? Is the nucleophile part of the rate determining step for SN2? Yes. Is it part of the transition state of the rate determining step? Yes. Will it affect the rate? Yes. How? Stronger nucleophile, able to kick off the leaving group, reaction goes faster. Now let me ask the next question then. My next question is going to be for SN1. How does a stronger nucleophile affect the rate of an SN1 reaction? Faster, slower, same. Has everybody answered that can answer? Oh. We have a split. So for SN1, what's the rate determining step? For the rate determining step, it's going to be the alkyl halide or the molecule losing its leaving group to form the carbocation. That's the rate determining step, right? Yes. Is the nucleophile part of the rate determining step? No. So it turns out for an SN1 reaction that you can use a better nucleophile, but it's not going to increase the rate of the reaction. The rate of the reaction is totally based on this first rate determining step. And so what's it going to be based on? Well, it's going to be based on leaving group ability, and it's going to be based on the stability of the carbocation. Right. With what kind of halide reacting fastest? Primary, secondary, tertiary. I hope everybody's just exhausted. Been planning for, remember, Halloween is the most dangerous holiday of the year. You have to be wise in your choice of costumes. Probably would be best to go no costume to avoid all of the stuff. But can I get 5 minutes? Which one's the fastest? tertiary halide. Now, if you go back and you look at the last question on the first exam, that question, given what we've talked about now, should hopefully be kind of a piece of cake to answer, because now we've talked about the details in terms of SN1 and SN2 reactions. If you remember, go back and look at that, I'm basically asking these kinds of, I asked that kind of question back then. So it was kind of like, well, which product's more stable? Or which intermediate's more stable? And it was a tertiary versus a primary carbocation. And so the tertiary being more stable is the one that's going to form fastest. Why? Because the Hammond's postulate and all of that stuff. So if I want to see whether or not you now understand that, I could put a question like that on the next exam to see if now we can put all that together. But that's how we're doing this faster, slower, same rate type of analysis. Because ultimately, here's what I can do. Oh, let's see, what's a good one? Let's say I give you this reaction. There are these two reactions, A and B. And I say, which reaction is faster, A or B? Or C, same. So which one's faster, A, B, or C would be they'd have the same rate? And if you've answered the first one, take a look at the next two, because we're going to go right down the line here. So for A, which one is faster? A, B, or they're the same rate? Another couple seconds. Okay. 22 say B. Why do you say B for the first set of reactions? Because BR is a better leaving group. Okay. So we really kind of need to think about the whole. Well, let's move on to the next one, and then I'll sum up here at the end. All right, next one. A, B. Which one's faster, A, B, or same rate C for the second set? Okay. Oh, we're split. The major answer is B. B reacts faster. Okay? Last one. A, B, which one's faster, A, B, or the same rate, C? One. Going once, there. So, looks very similar. Right, that's fine. So, how do we approach these problems? What's the first thing you need to know? You need to know mechanism. Now, I cannot mix mechanisms. So they both have to be SN1 or they both have to be SN2. I can't have one go by 1 and one go by 2. That's apples and cars. Not the same. Can't compare them. Then once I know what the reaction mechanism is, then what am I looking at? I'm going to look at the difference. What's different about the two reactions? And then what's different? Okay, now let's put that in the context of the reaction. Okay. So that's how you want to approach these kinds of problems. And I know there's some in the chapters. Okay, so what we will do, I didn't do anything today that I had planned in the reading because I wanted to catch up on SN1 and SN2 that were in chapters 7 and 8. We were going to do E1 on Monday. We'll do some carbocation rearrangements. So that'll stay the same, but I'll push E1 to after the exam. So I'll rearrange the Canvas reading lists. Anything on the roadmap that says E1 is not going to be part of the exam. So Chapter 9 will not be part of the exam. I do have a take-home quiz. It's right here. You can grab it. It's writing the mechanisms of an SN1 and an SN2 reaction. So that'll be due at the beginning of class on Monday. So pick one of those up on your way out.
When is the chapter 8 homework due?
The